Right, so now we have done bulk of your syllabus. Now we have to do more past papers and bit of theory as well. Okay, so today we are going to do some past papers as well as a bit of theory. Okay. So again I'm refreshing you, right, almost each day. Right, so we discussed the general architecture, the von Neumann architecture. Okay. Uh, the importance of memory, because everything has to go through, first come to the memory and go to the processor. Okay, so we discussed that, and also we discussed the memory related things. You can think of memory as a grid where you have address and the data. Both data and instructions or the programs will be in the memory, but in two separate areas. We discussed the concept of byte ordering, the big endian and little endian, and also the addressability, that is the byte addressable and word addressable. If one location is not enough, you have to go for consecutive locations, right? That is byte ordering. Addressability means sometimes you can go for 2 bytes, 3 bytes in one location. Your memory is can be used like that. But it's very important thing is there, that is there's a concept called physical memory and logical memory. I briefly explained it last time, so today I'm going to again explain it. Okay, because there were some questions related to that, that's the memory translation as well. Okay, so therefore, so today we are going to do some past papers also. Right, so then we discuss about the memory segments. So different things are in different areas, like the OS reserve 2 areas, then the text area where your programs running programs loaded, then the data segment where your data or the local data is there, then the stack, the method calls and other data is there, and heap, that is the where the objects are created, that is the sort of a global area. Okay, so if you have any questions on these topics, you have to ask. Okay, of course I'm not expert in computer system, but as long as I can, I will explain you, right? So don't keep anything, if you don't understand, you have to ask. Okay, so you're final year and this subject is not that easy, I told you, right? But this is not impossible subject if you understand. Okay, right? So if you have anything to clear from these areas, you have to ask. Okay, right? So then we discussed the concept of virtual memory, right? So we can borrow part of the secondary storage as an extension to the physical memory. Okay, so therefore your program sees a bigger area than physical memory, right? So the physical memory is a small, say in my computer I have 8 GB, but my program see it as more than 8 GB, maybe 12 GB. So therefore there's a mapping is needed between the logical memory and the physical memory. Okay, logical memory and the physical memory. So that is done through the page translation table, right? Page translation table. So I promise you to give you the note on memory address translation. I forgot. Okay, so basically I will be sharing you the A-level ICT note, so that note has that memory translation. Okay. So I'm again explaining you because today we are going to do some past papers and I need those things. Okay. So anyway, I will forget to again upload. I will put it into your WhatsApp group also. Otherwise, always I forget to put it into the. So don't think that this is A-level ICT note. Hari api hari doku final year jadi tan apa? Wah kiyo kan hari. මොකද දැන් ලංකාවේ A level කියන්නේ කොහොමද එකක්ද කියන්නේ නේද? Right. Right. So today I'm going to first go through this note because you have to understand the process transition as well, because I found that there are some questions related to that also in your paper. So let's do it. Okay. Right. Because they have asked some questions in your paper. Okay. Right. So right, I'm not going through these classification of OSs, etc. You have done this in semester 1. Okay. So multi-use, now remember, single use single task, single use multitask, right? Multi-use multitask. Those are the three main categories. Then of course we have the real-time operating systems. Real-time operating systems, because you must know these terms, because the moment you open your paper, you will see these terms. Okay. So multi-use multitask. You can see multitasking environment, right? You can see multitasking operating system. So you must aware of these terms. Okay. So for example, Windows is a single use multitasking environment. If you take all DOS operating system, it's a single use single task. But if you take something like Linux, it's a multi-user multitask environment. Multiple users can access the computer and they can do the multiple tasks. So each user is allocates different memory. Okay, but Windows is not like that. You have to log off. One user has to log off in order for another user to log in. You can have multiple user accounts, but not multi-user. Okay. Of course, then you have the real-time operating systems. Okay. And embedded operating systems, etc. Of course, that is not something they will check in your final year, right? So then this is very important, right? So you can have the multiprocessors, right? So this is මේක අර A level ICT students කට හන්ද බොහොම පොඩි අයට වගේ explain කරනවා. හරි. ඔයගොල්ලෝ පොඩි අය නෙමෙයි හන්ද ඔයගොල්ලන්ගේ note එක high level එකේ තියෙන ඒගොල්ලන්ට. හරි. ඔයගොල්ලෝ finally ඉන්න කට්ටියනේ. නමුත් මෙතන තියෙන එක ඔයගොල්ලන්ට අදාළයි ආ. And with the ඊළඟ topic එක මොකද multiprocessor systems. So therefore this is a good starting point for that, right? So you can have different possibilities. Okay, so remember we want to speed up the computing, right? Speed up the processing. So in order to speed up, so there are places we can speed up. One thing is increase the processor speed, the clock speed. Okay, but there are limitations. So another thing is, why don't we go for multiple processors, right? Rather than running on one processor, we can have multiple processors. Okay, so here you can see this is one processor, right? This is another processor. Two processors in the motherboard. So that is called multiprocessor. Okay, now most of the computers have now two processors, the central processing unit and graphic processing unit. So that is also sort of a multiprocessor, right? And also you can have multiple, not graphic processing unit, multiple processors also. Okay, so that is one way of increasing the performance, especially when it comes to high-end computers like servers. Okay, right? Multiprocessor. Physically, you have multiple processor chips. Okay, multiple processor chips, and different applications can be executed by different processors. So they have their own cache, etc., own registries, etc. So that is one option. Speed up. Okay, speed up your processing. Another option is you can have multi cores, right? So this is obviously single processor, single core. So that is single processor and single core. Okay, so these days you don't find single processor, single core, single core processors much. These days what you see is single processor, multi-core, right? Single processor. Now here multiprocessor, but this is single processor, but that single processor, the operating system see it as multiple processors. just physical processor, chip, but operating system see it as multiple cores. Actually, not only operating system see it, in that single chip, physically there are multiple processors. Here separate processors, just one processor chip, but inside that chip there are multiple physical processors. So then we say multi-cores, right? Multi-core. Core means physical processor. For example, in my case, my computer has 2 cores. So it's a dual core processor. Right? If I go to the CPU, you can see here. Right? Core. Yeah, you can see cores 2. So you can clearly see there are 2 cores. Right? Two cores are there, right? So that means I have one processor, right? I have something like this. I have one processor chip, but inside that processor chip there are 2 physical processors of 2 physical cores. Okay, so that is called single processor multi-core. Then there's another option. This particular core, that is a physical processor, can be visualized or seen by your operating system as multiple logical processors. Logical, it's as a logic, right? So then in my case, one core is seen by the computer or operating system as one core is seen as 2 logical processors. Okay, so again, if I go to the task manager and processor, you can see here 2 cores, 4 logical processors. So that means 2 cores, 4 logical processors. That means each core is seen as a logic by your operating system as 2 logical processors. So therefore, my operating system, my Windows see this processor as 4 logical processors. It has 2 physical cores. It is in single chip. If it is in multiple chip, it's a multiprocessor. This is not a multiprocessor. This is a multi-core. That is why dual core. One processor, multi-core, right? That is dual core. But each core is seen as 2 logical processors. Therefore, my operating system sees it as 4 processors, 4 logical processors. Okay, so I am saying that my computer is a single processor because my other processor is a graphical processor. It's not a normal CPU. So right. So this is my GPU. So it is a dedicated thing, right? It has only one particular task to do, that is graphic processing. Okay, that is graphic processing. Okay, right. So now you must understand what is meant by single processor, multiple processor. A single processor can have multiple cores, that is physically multiple processors. Each core can be seen by the computer or the operating system as multiple logical processors. Okay, right. So other than that, your computer can do few more things to speed up, right? So your operating system can execute multi-threading. So that means the operating system can execute multiple threads in your processor. So then we say it is multi-threading. Allow multiple threads of sub-processors to be executed using time sharing. So this is given time slot, then this one again time slot. So these threads are running, so we feel like multiple programs are running, but in reality one thread is run at a time in time sharing manner. Okay, then we have hyperthreading also. So hyperthreading means each physical core is subdivided to multiple logical cores. That is what has happened in my computer, because my one physical core is seen as two logical processors, and each thread is concurrently executed by different logical processors. Now remember, I have two cores and each core is seen as two logical processors. So hyperthreading means these threads are given to these different logical processors. So this logical processor is executing this one, this logical processor is executing this one. So that means now they are parallelly executing, right? But in reality it is not parallelly executing, because these two logical processors are one physical core. So then we say it's a hyperthreading, right? Hyperthreading. Okay, right. So the multithreading and hyperthreadings are related but two different things. Okay, so each thread is, or these threads are allocated different logical processor means hyperthreading. Multithreading can happen even without hyperthreading, right? So in that case, it is a time sharing manner. Your programs are executed. Okay, right. So you can see so many words are there: multiprocessor, multi-core, multiple logical processors. Then of course there's another one called hyperthreading. Okay, hyperthreading, and of course the multiple threading. Right. So file handling, I am not going to do with you because this is a A-level ICT note. Okay. But if you have anything that you want to extract, you can get it. Okay. Right. So these things are not covered in your exam paper. No, these are not part of your exam paper. But they can ask about file control blocks. Okay. Because they have asked about process control blocks. I think last year or the previous year. So therefore they can ask about file control blocks. So file control block means your operating system maintains meta information about your file, right? Last updated date, file size, right? File name. Okay, so privileges. If it is read by a program, what is the last access position, etc. So that is called file control block, FCB. Okay. Right. So anyway, they are not going to ask about these things. They are not going to ask about this defragmentation. Right. So process management. So there was I think 2019 paper there was a question on this. Right. So when a program is running, we call there's a process. Right. So running program is called a process. Okay. Now for example, my PDF reader is running, right? My Edge is running, Edge browser. WhatsApp is running, right? So this recording, OBS Studio is running, and so many things are running. Even my OneNote is running. So those are called what? Now there are so many processors. Right? If you go to the task manager, go to the processors tab, you can see all the processors which are running right now. Right? All the processors, so many processors, right? More than 100. Right? More than 100 processors are running. Okay, and some processors have sub-processors as well. You can see. So because I have opened so many tabs, right? You can see now some of these sub-processors will be closed. Okay, and memory will also be released. Right. So running programs are called what? Processors. Right. Right. Now I told you that the Windows is a single user multiprocessor single user multitasking environment. Forget about multiple processors or multiple cores or hyperthreading or whatever. How does computer do or how does computers do multitasking in a very innocent single processor, single core, single logical processor, no hyperthreading environment. How does computer do the multitasking? Anyone can anyone tell me? Because this is a very simple question. These things you must know from your school level. How do you call it? Anyone? Just one word will give it. දවල් ඉන්ටර්විව් එකට එමෙ යන්න අදහසක් නැද්ද? ඔයගොල්ලෝ පස්සේ දොරවල් වලින් ජොබ් වලට යන හිතන් ඉන්නේ. ජොබ් කර සමහරන ජොබ් කරනවා. නේද? පස්සේ දොරවල් වලින් ගිහිලා තමයි රටට කෙලවිලා තියෙන්නේ දැන් නේද? ඔයගොල්ලෝත් එහෙම යන්න හිතන් ඉන්නවද දන්නේ නැහැ. පස්සේ දොරවල් වලින් එක එකාගේ පස්සේ පැත්තේ ගිහිල්ලා. So how does computers do multitasking? So they do the multitasking by time sharing. Time sharing. Each process, each running process is given time slot. So now this is executed. So this is the execution. Now we stop it. We give it to the other one. We stop it. We give it to the other one. Now again this one, this one, this one. If this is now done, of course now it is done, but still this one is running. Maybe another one start now. Right? So we call it time sharing. Actually only one process is executed at a time if it is a truly single processor environment, but we feel like multiple programs are running because we call it context switching. Context is switched from this to this to this, and this to this, back, and now you can see all are sort of a proceeding at the same time, but in reality they are not proceeding at the same time. They are given small time slots. Okay, so that is called context switching. So this context switching is managed by operating system. That is one of the key tasks of operating system. Okay, that is one of the key task of operating system. And of course if it is a multiprocessor or multi-core, then while these things are happening in a single core or single logical processor, same thing is happening in another core or another processor. So therefore yes, they are truly parallel processing. At a time more than one instruction is executed at a time in a single clock cycle, because either you have multiple processors or multiple cores, then yes. But if you look at one core, still this is happening. Inside one core, this context switching is happening. Okay? Right. So this diagram is extremely important. This diagram we may have done in semester 1. I am not very sure whether we did it for you guys. The process state diagram. Okay, process state diagram. So this is a very famous question in A-level ICT paper, right? So A-level ICT paper, structured paper, they only frequently ask these things, right? So this diagram is extremely important, and in your paper also I found some questions related to this one, right? So when a program, now when you click on a program, say something like you click on this, sometimes it is not automatically appearing. If a lot of programs are running now, right? So we say that when you run a program, it goes to the new state, right? It goes to the new state. Okay, so there will be some waiting. There's something called process scheduler. Scheduler is the one giving you the time slots, giving each process running applications or the processors the time slots is given by scheduler. Right? So sometimes scheduler is busy. Therefore, scheduler has not given you the attention. Though you have clicked on the application, still you are in the new state. Still you are in the new state. Okay? So that is why sometimes when you click and open a program, if you are really struggling with memory, sometimes it takes maybe 10-15 seconds to appear that initial screen, because it has been there in the new state for some time, because the thread scheduler has not given attention to that one, because it is busy executing other things, right? So once the thread scheduler is free, that newly executed program, newly run program will be taken to the ready state. We say that it is admitted to the ready state. It's something like admitted to the hospital. Still no one has given you the attention. Once you admit, yes, the hospital staff is going to give the attention to the patient. Same thing, now your process has come to the ready state, or has admitted to the ready state. Ready means now it is ready to be executed, or it is a candidate for to be executed in the processor, whatever the logical processor, or the whatever the core, or whatever. Okay, the OS will decide to which logical processor this particular process is given. Now there are some programs in the queue, running programs, so processors in the queue to be executed. Maybe some of those have half executed, and they are back in the ready queue. Now new program is also coming to the queue now. Now we say they are in ready. Okay, ready state. So ready means ready to execute. Now your thread scheduler, which is part of your operating system, it will pick one at a time and put it into the running state. We say that it is dispatched to the running. So one of the thread will be put it into the running state. If the thread has executed up to this point, now it is again executes from that point to another. It proceeds for some time, right? It may not be given the full execution, because lot of program processors are waiting. So after executing for this one for few clock cycles, right, again it will be put back into the ready state. So once it's time out, maybe it is given 100 nanoseconds. Now 100 nanoseconds has passed. Now now the thread scheduler put it back into the ready state. Why? It want to give a chance to another ready state process. Now that one comes to the running state. The previous guy is again in the ready state, and newly admitted threads will processors will also get that attention, right? When it is giving the attention, it will try to give everyone attention, every process attention, equal attention. Okay, unless you have the high priority processors, there's something called priority also, right? So there you can increase the priority, right? You can say, where is that? Maybe properties, where is that? Maybe somewhere. So there should be a way to give you the priority. Yeah, you can see set priority, right? You can, so usually the high priority processors will be given little bit more attention, okay, but otherwise they will be given the same attention, right? So anyway, whether it's high priority or low priority, the processor is going to give each and every process attention, sort of equal share. Okay, right? So now you can see that your running program is frequently going to the running state, coming back to the ready state, running state, coming back to the ready state. So gradually now it is getting executed. Okay, so once it is done, execution is over, it goes to the exit state. So there are so many possibilities where it can go to the exit state. One possibility is naturally your program has now finished, completed. Now it has to go from running to the exit. Or user has closed that application or terminated. Again it has to go to the release. Right? So you can terminate, right? You can For example, I can close this, right? So then it's terminated. Or some exceptional situation has occurred and now program cannot proceed. Therefore, your operating system may decide to abruptly terminate that also. So that is another possibility of going into the exit state. Right? Now you can see that it comes here, it goes like this and it goes to the exit state. Okay. But while this is happening, there's another possibility. That is, when your program is running, there can be a situation where now user has to give you some input, or user has to click on button like OK or cancel. Now until the user give that attention, we cannot give no point giving it another time slot. Okay. So therefore, in that kind of a situation where your application is waiting for user interaction, your operating system is taking it, rather than putting it to the ready state, it is putting it to the block state. So block state means it is waiting some user event, right? Block state. Because no point giving it another time slots until the user has given the attention. Usually user attention need take some times, right? At least few seconds. So therefore, when that kind of a situation is there for your running process, the OS will put it into the block state. Okay. So once the user has given the attention, that input to output attention, now again it is going from block state to the ready state. It can never go to the running state directly. It is now again joining the ready queue. Right? Now again OS can give you the chance, because now again you are back in the ready. Okay. Again you can go through like this, right? And maybe once it is done or terminated or error, you go to the exit state. Okay. So now I have explained this portion. Now you must not have any question about this portion of the process diagram. Okay. Right. So then there's another thing can happen. That is, I told you that when your computer is running out of memory, your computer can write the part of your physical memory into the secondary storage, or we call this virtual memory. Why does your computer want to do that? Because you have started another program and somehow your computer try to execute that one also. Execute that one, you can't execute it without loading it to the memory. Now memory is pretty much full. So that is always the case when in my computer, almost all the time, pretty much full. You can see my memory is pretty much full. So that means definitely it is using, because it's always keep a buffer area, right? So that means it is heavily using my secondary storage. That means my SSD is also used as extension to my physical RAM, right? So when that kind of a need arises, it has to decide which running program memory segment I want to put it into the virtual memory or the secondary storage, right? Because if you want to load something else to the memory, we have to put something else, some other thing into the secondary storage to take that space. So maybe you are in the ready state. Now your operating system might decide your process to be part of your process to be put it into the secondary storage or the virtual memory to give some other programs the physical memory. So then your operating system will put you into the ready suspend state. Your process was in the ready state waiting for the execution, but because of the memory shortage, now your operating system has despicked your process to be put it into the process, in the sense your program or pages in your program to be put it into the secondary storage. So therefore, when that happens, your operating system will put your that process from ready state to the ready suspend state, right? Ready suspend state. Once that memory or once that program is executed, though sometimes your operating system will decide, okay, now I have taken care of that particular program for some time. Now I want to take this guy again and give this guy also some time slots. So therefore, in that case, in that kind of a situation, again you are taken from ready suspend to the ready state. Now you will be get time slot to go into the running state, and maybe you will be able to finish it as well. Oh, still you are running, right? So when you are putting into the virtual memory, at some part of your things, you are in the ready suspend. When you are taken back to the memory, physical memory, now again you are in the ready state. Again now you can go to the running and ready and running and ready and maybe finish. Okay, right? So this can happen not only you are in the ready state. This can happen when you are in the block state as well. Now block state means you are waiting for a user interaction. Right? So while you are waiting for the root user interactions, operating system may decide, okay, now I am going to put you into the virtual memory. So then that process is moving from block to block suspended. Right? Suspended means virtual memory. You are in the virtual memory. Okay. Block suspended means while you were in the block state, you are taken to the virtual memory. Ready suspend means while you were in the ready state, you were taken to the ready suspend state or the virtual memory. Okay. And there's a higher possibility that these things will be taken to this one, because when you are waiting for input output user interactions, right? So this guy is at least ready to do, right? Therefore, there's a higher likelihood that these block state process will be taken to the block suspended. Okay, right? Again, when that memory problem is resolved, now you can go back to the block state. Right? Memory problem is solved, but still user has not given the attention. When the user gives the attention, it goes from block to the ready state, right? So another thing can happen. Now you are in the block state, waiting for user interactions. Then came the memory limitation. So therefore you were put into the block suspended. While the memory issue was there, and while you were there in the virtual memory, maybe the user has given the attention. Now user has given the attention and that particular thing is done. Now still the memory issue is there. Therefore we can't take you to the physical memory yet. Then it will be taken from block suspended to the ready suspended. So ready means now you are ready to be executed, candidate, but still you are suspended because of the memory issue. Now once the memory issue is resolved, you will be taken back to the ready state, and again you will be getting the attention. Okay, that is what happens when a programs are run, right? So your program can go into any of these states, or sometimes only happy path and done. Sometimes it might come here, everywhere at different times. Okay, so that is called process diagram. Okay, so any questions? No? Right. So I'm not going into details. I'm just doing enough thing for your exam. Right. So then there are two type of context switching. Right. So we need to understand that also, because now we are moving to the multiprocessor environment. Okay, right. So the preemptive context switching versus non-preemptive context switching. Context switching means you are giving attention to different processors, right? That is called context switching. So this context switching is a necessary. Otherwise, user don't feel like things are happening parallelly. Actually, things are not really happening parallelly, but user feel like things are happening parallelly. Okay. So therefore, this context switching is needed, but this context switching has a disadvantage as well. The moment you go for context switching, there's overhead. What is that overhead? Now this has been executed up to this point. Okay. Now we are going to context switching and give attention to this thread, this process. Now next time again we have to start from here. Start from here when we are coming back to this thread again, this process again. So therefore, when the context switching happens, your operating system has to save all the current situation. What is the current situation? If there were some values in the registries, you have to save those registry values. And also it has to keep track of which particular instruction or the program counter value, which instruction was last executed. Right? Why? When it is given the attention back, context back, now again the registries must be initialized. Now it has to load the next instruction. So it's overhead. But it's overhead, but it's a necessary overhead. Otherwise, we can't do this parallel like processing or multi-processing. Okay. So therefore, but there's an overhead also. Every time there's a context switching, there's a waste of time as well. So therefore, we don't want to do it unnecessarily. Also, we have to find out which frequency is the best for the output and user experience. Okay, right. So when it comes to context switching, there are two strategies: preemptive context switching and non-preemptive context switching. Okay, so preemptive context switching means each process is given fixed time slice. Say every process is given say 100 nanoseconds. After 100 nanoseconds, this process will be suspended or put it into the ready state. Not suspended, put it into the ready state. Now next one is given. Likewise, your processors are given fixed time slots. So then we say preemptive context switching. Okay. So preemptive context switching is good because every process is given sort of a equal opportunity. Oh, they are given the attention, right? All the processors get some attention, right? So that is the advantage of preemptive context switching. But there's a disadvantage. Disadvantage is when you give fixed time slots, we need to do some frequent context switching. I told you that every time there's a free context switching, there's overhead. You have to save the current values, etc. So therefore, usually for preemptive context switching, the overhead is also high. But user will feel like parallel things are happening. But at the same time, there is a overall performance issue as well. Slight reduction. Okay. Right. So there's another approach, non-preemptive context switching. So non-preemptive context switching means when your operating system or the thread scheduler or the scheduler, process scheduler give attention to a particular process, usually it will continue to give attention until it is done or it reach to a interrupt or something like user attention, right? That means it's sort of a suspended, right? Until it's done or it goes to a sort of a suspended state or the user attention state, it will be given the time. Right? So once it is done or in a suspend state, and now it is giving the context to another one. So likewise, it will give bigger attention to longer attention to the processors. So then we say it's a non-preemptive context switching. The overhead is less because there will be lesser context switching, but some processors may take up a lot of attention, preventing other processors to proceed. That is a disadvantage. So usually operating systems do mixture of both, right? bit of non-preemptive and preemptive mixture. For some processors, they try to give non-preemptive. For some other processors, they give preemptive attention. And again, though we say it's not 100% non-preemptive. If some process is taking too much of time anyway, it will be giving that attention to the next guy as well. Okay, right. So that is the difference between preemptive and non-preemptive. Right. I told you about file control block. So similarly, there is something called a process control block. I think they have asked about this in your paper. You can see what is a process control block. ඔයගොල්ලෝ හිතන්න බෑ මම මේ A level ICT note එකක් අරගෙන මේ විකාර කරනවා කියලා හරි මට අමාරුවක් නැහැ නේ ඔයගොල්ලන්ට A level ICT ගන්නන්න හරි මේක ඔයගොල්ලන්ගේ note එකේ නෑ කොහෙවත් හරි මේ කොහෙන් හරි කමන්නේ ඉගෙන ගන්න A level ICT නෙවලින් නෙමෙයි ශිෂ්‍යත්ව පන්තියකට හරි ගිහිල්ලා කමන්නේ විභාගේ පාස් වෙනවා නේ right so process control block. So I told you that every time when there's a context switching, right, you have to save what is the current states, right, of that process, because now again the next process is going to take up the processing. So the registries and everything are going to be filled with the next other processors in instructions and data. So therefore, when you are taken out of the running state, your operating system will write the current state and current data values in the registries to something called process control block, PCB. Okay, so your PCB will have some data, some important values. Of course, it will be having what is the current state, because sometimes, most of the time, of course, the current state will be running, and now we are putting back the ready state, right? Ready state. Okay, but while you are in the ready state, if you are put into the suspended, okay, so that means waiting for the memory in the virtual memory, then it will be say the status will be suspended. Of course, if you are put into the blocked after running because of the user interactions needed, so then it will say the current state is blocked, right? So what is the current state? Then the process number, because every process is given a number, right? Here you will see that every process is given a process number. So you will see it somewhere here, right? Process ID, PID. So that PID will also be there. Okay, PID will also be there in your process control block, right? So process state, process number, and program counter. So program counter is, remember when we were discussing the general purpose registry architecture, I think last week or the week before, I told you that there's something called program counter. That is, this is the instruction registry, decoder, ALU, the general purpose registries. Then remember we have program count, instruction registry, decoder, ALU, your registries. Now this once it is decoded, it always upload the program counter before sending it to the ALU. So the program counter has the memory address of next instruction. So it has to keep that also, because remember, once it is given the attention, your operating system must know which instructions to be fetched when it is given the attention, right? So therefore we have to give the program count also, right? What is the process state? What is this process? What is the program count? And all the registry values, current registry values it has to save, because once it is given the attention, these values must be again restored to the registries. Then the memory limits, right? which memory areas are related to this particular process, especially the data memory areas, and are there any open files, right? Because there maybe it was working on some file operation. Then once it is given the context, it has to continue with those file operations, right? Again, continue with those file operations. Therefore, what are the open files and up to which point you have read it or something like that. Okay, those informations are kept in a data structure called process control block, right? So it is used every time it is taken from running to the ready. This is written. Every time it is taken from ready to the running, this is read. Process control block is read. Okay, right. So I explain you the this one. Okay, right. Now let's do this question. The question ටිකත් එකේ ඉවර වෙනවා නේද? Right. Yes.
Process control block also in the RAM. Is it?
Yeah, everything. Yeah, everything must be in the RAM. Yeah, process control block is also in the RAM. Yeah. Okay. So because operating system is also in the RAM. So therefore, operating systems, whatever it needs to do, definitely process control block must be in the RAM, because it is something that frequently needed. Every time context switch is done, the process control block must be consulted. So therefore, it must be in the. So that is why your operating system is also reserved memory, right? So for those kind of things, other than the operating system related files, those are the things that the memory is taken up. Okay, right. So what is process control block? Explain the involvement of PCB when a context switch is made from process PC to P0 to process P1. So now I hope you can write that answer, right? PCB is operating system data structure, right? It's managed by operating system. It's a data structure that keeps information of process, right? That keeps information of process. When a context switch is made from P0 to P1, CPU state information, example content of the registry is related to P0 is stored in the PCB for P0, so that when P0 is restarted, it can start from the place where I stopped, right? So load the machine registries with the relevant information that is stored in the PCB of P1, so that P1 can start the correct place. Now read the P1's PCB and start again the P1, right? So you better write the structure of PCB as well here, at least the processor state, blah blah blah. Okay, so that is something you can do to make it much more clear. Okay, right. I hope you can answer that question. Okay, so that part is done. So that part is done. Okay, right. That is 2020 paper, I think. Okay, right. So let's keep on discussing our things. Right, managing memory. So these things I explained you last time. Okay, these things I explained you. What is little endian, big endian, memory segmentations, the virtual memory, right? Memory address translation. So this is very important topic. Right, I told you that there's something called physical memory. That is the real memory, your RAM. And there's something called logical memory. Logical memory means what operating system sees as a memory space. That is exactly what your programs also see, right? But that is a logical thing, right? Sometimes we call it virtual address, but the proper name is physical memory, logical memory. So physical memory, you have the physical addresses, that is your hardware addresses. In logical memory, you have different addresses, right? To the same memory, physical memory address. Say it's keeping some data. Maybe the physical address is 01011. The logical address can be completely different address 0110111, right? And now usually this address is longer than this one because logical address space is bigger than the physical address space. So therefore definitely if this is 8 bit, this is usually at least 12 bit, 16 bit, because we need more memory locations, because logical memory is bigger than physical memory. Okay, මම මේ කියන හැම වචනයක්ම වැදගත් එක්සෑම් එකේ questions වලට answer කරද්දී හැම වචනයක්ම. Okay, right. Now when it comes to the memory width, this is always 1 byte. This is always 1 byte. හරි වැදගත්. ඔක දෙන්නේ නැහැ ඒගොල්ලෝ අය. Physical memory එකේ එක byte එක ගානේ තමයි තියාගන්නේ. But here it can be variable. And it can be varied. Okay? Logical memory. But physical memory we always take it as 1 byte. Okay? Right. Now there must be a mechanism, right? Because programs and everything is referring to these logical addresses. Okay, but these are logical addresses. There is no physical memory address like that. So therefore there must be a way to transform or convert your logical memory address into the real physical memory address. Okay, so that is called memory address translation. Memory address translation. So this is your logical address. Now some people call this logical address as virtual address as well. So therefore don't confuse. Here virtual means again logical address. But you know that you have the physical memory and logical virtual memory. All together we call it logical. So this is physical memory, your RAM. This is virtual memory borrowed from your secondary storage. All together we call it logical memory. But in general, this logical memory is sometimes, entire logical memory is also called virtual memory. And this address is called either logical address or virtual address. So sometimes you get confused, right? So therefore this virtual memory is used, name virtual memory is used for the real virtual memory as well as in general logical memory also we just sometimes call it virtual memory. Okay, so don't get confused. I know it's confusing, but because of the ways people are using the same words, but you must know that sometimes when they say virtual memory they refer to this, sometimes they refer to this entire logical memory as virtual memory. Okay, right. Now how do we do this translation? Actually it is done by your operating system. So I told you that when it comes to physical memory, each 1 byte get a physical address. So that is extremely important, right? Every byte get a address. But when it comes to logical memory, it is not necessarily every byte. Sometimes every 2 byte, right? Every 4 byte get an address. Okay. Right. So now we are moving to this memory address translation. Right. Memory address translation. How does your operating system do this, or does this translation from logical memory to the physical memory? Okay, logical memory to the physical memory. So it's little bit complex thing, but of course you must be having the potential to understand this. Of course if A-level ICT student can understand, why can't, how do you say you can't understand, right? And this memory address translation is a very popular question in A-level ICT paper, structured paper, right? So operating system maintains something called page table. So that page table has the mapping between your logical memory page to the physical memory frame. Now I am using two terms, page, frame, right? So in your logical memory, that is a conceptual memory, your operating system break your logical memory into portions, equal parts, and we call them pages. One page, this is another page, so right. So your logical memory is subdivided into pages, page 0, page 1, page 2, page 3, etc. Okay. So when it comes to your physical memory, right, again we subdivide it into the same size. If this is this much, your physical memory also be divided into same size portions, right? And then we call it frames. So here we call it page, here we call it frame. There's a very important thing, that is page size is same as frame size. Right? Page size is same as frame size. Okay, page size is same as frame size. So why? Your pages must be able to fit into these frames. Now you can see this page 0 is here. This page 1 is in frame 4. Page 2 is in frame 3. Right? Page 2 is in frame 3. And page 3 is in frame 7. And there are some physical memory, there are some available. Right? Now here we have plenty of physical memory. So therefore it is not using any virtual memory. It is not using any virtual memory because there are plenty of vacant areas also. So your operating system keep track of which page is in which frame. Right? Page 0 is in frame 1. Page 1 is in frame 4. Right? Page 2 is in frame 3 and page 3 is in frame 7. Okay. So that is what operating system is doing. It keeps this page table. It keeps this page table. So here we call them pages, here we call them frames. Your pages will fit onto frames. So therefore page size must be same as frame size. Operating system will keep track of which page is in which frame. Okay. I hope you can understand up to that point. Right. Now there is a problem. I told you that the physical memory is smaller than logical memory, or the physical memory space is smaller than logical memory space. Your physical memory can be 4 GB, but your operating system will look at the memory as 6 GB. Why? Your running programs demand more than 4 GB. So therefore operating system will show it as a not 4 GB memory, 6 GB memory to your programs. Okay. So then how does your computer do that? Operating system do that by taking some storage from the secondary storage also as an extension to your physical memory. So therefore these physical memory plus the virtual memory will be your logical memory. So therefore physical memory you will see it as something like this. Say assume that each one is 1 megabyte. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? Now physical memory is 11 MB. But your logical memory is 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Your logical memory is 19 megabyte, whereas your physical memory is just 10 megabyte. Why? 9 taken from the secondary storage. Okay, so therefore you can see that logical address space is bigger than physical address space. Right? Still we have to map it. Still we have to map it. So how do we map it? So still we use the page table. Right? Now you can see that your page A, right? Page A, oh, this is the zeroth one, right? Zeroth one. So the zeroth page is in zeroth page is in fourth frame. Now you can see fourth frame, and this is called valid invalid bit. If it is in the physical memory, it will keep it as valid because it is in the physical memory. So therefore it is valid. Now what about the page 1? Right? Page 1, it is B. Now you can see that B is not here. B is not here. So therefore it is not having any frame number because no frame number for B page. You can see B is not there. So this will be empty, and here it will say invalid. So that means this page, if you are looking for address in page B, no, it is not in the physical memory because it is actually in the secondary storage or the virtual memory. Then what about the second page? Second page is C. Yes, C is in the frame 6 and it is valid. What about the third one? D. D is not there. It's invalid. Fourth one. E. E is not there. Invalid. Invalid means it is in the virtual memory or secondary storage. 5. 5 is F. Yes, F is there in the ninth one and it is valid. And of course G and H is not there, so they are invalid. They are invalid. So only valid things are these three. Right? Others are in the secondary storage. Right? Then හරිනම් මේ ACD ACF කියන තුනට මෙතන ඉන්න බෑ හරිනම්. හරි. එහෙම ඉන්නත් පුළුවන් මෙතනත් ඉන්නවා මෙතනත් ඉන්නවා. ඇත්ත කතාව දෙන්න මේවා දැන් වේකන. ඔය මේවා මෙහෙට අරන් ඇවිල්ලා තියෙනවා. මේ ඉන්නේ ඇත්තට මේ තුන් දෙනා. හරි. BD තමයි මෙතන ඉන්නේ. BD E FGH තව තියෙනවා. හරි BD FGH වගේ. FF නෑ GH මෙතන ඉන්නවා නා. GH වගේ. හරි. ඔය දෙගොල්ලෝ ඉන්නවා ඩිස්ක් එකේ. Right. So I hope you understand that also. කොතන හරි තේරුම් නැත්නම් ඒ වෙලේ කියනවා මට මෙතන තේරුන්නේ නැහැ දැන් කියලා. හරි. ඒතර එක්කම එක්ස්ප්ලেইন කරා නැත්නම් මාත් කියන මට තේරුන්නේ නැහැ වැඩිය. මාත් මේ බොරුවක් තමයි කිව්වේ කියලා. හරි. Right. තේරුම් නැත්නම් පටස්කාර කියන්නේ. Yes.
Secondary storage means is it the hard disk?
Yes. It depends. For example, if your secondary storage is SSD, it's a SSD. If your secondary storage is hard disk, it is hard disk. දැන් කියන්න බෑ මගේ ගාව hard disk එකයි SSD එකයි දෙකම තියෙනවා කියලා. එතකොට ඔයාගේ virtual memory එක එයා ගන්න බොහෝ විට ඔයා configure කරලා තියෙන එකෙන්. Right? So for example, if you go to settings, සමහරවිට දෙකේම තියෙන්න පුළුවන්. දෙකේම තියෙන්න පුළුවන්. ඔගේ SSD hard disk දෙකක් තියෙනවා නම් virtual memory එකේ කොටසක් SSD එකේ තියෙනවා කොටසක් hard disk එකේ තියෙන්න පුළුවන්. හරි? මෙන්න මෙතන ගියොත් ඔයාලට පේන්නේ performance virtual memory settings. So here you can see කොහෙන්ද ගන්න කියලා මෙතන ඇති advanced වලට ගියොත්. So in my case it has asked to take this much of virtual memory. මෙතන ගන්න කියලා තියෙන්නේ කොහෙන්ද ගන්න කියලා මෙතන මෙතන C එකෙන් තමයි ගන්න කියලා තියෙන්නේ. D එකෙනුයි E එකෙනුයි ගන්න කියලා නෑ මගේ එකේ. හරි. මොකද C එකේ ඊට තියෙන අන්දා. C එකේ ඊට මදි නම් කියන්න පුළුවන් C එකෙනුත් අරගෙන D එකෙනුත් අරගෙන E එකෙනුත් ගන්න කියලා කියන්න පුළුවන්. හරි. ඒකට කොහෙන්ද ගන්න කියන එක ඔයා තමයි කන්ෆිගර් කරලා තියෙන්නේ. හරි. So මෙතන කියලා තියෙන automatically manage page file. automatically කියන්නේ යා operating system එක තමයි decide කරන්නේ මේක C එකෙන්ද D එකෙන්ද ගන්න කියලා. සාමාන්‍යයෙන් SSD එකේ ඊට තියෙනවා නම් යා SSD එකෙන් තමයි නැත්නම් system disk එකෙන් තමයි ගන්න. system disk එකෙන් තමයි ගන්න. හරි. ඒකන් තමයි ගොඩක් අයට වාගේ system disk එක මේ තව ඊට තියෙනවා. ඊට තියෙද්දිම සමහරවිට ඔයාලට පේනවා මේක red වල. මගේ පේනවා red කරලා තියෙන දැන්ට. දැන් මේ කියන්නේ ඇත්ත කතන්දරේ මෙයාට 7.16 GB ඊට තියෙනවා. 7.16 තියෙද්දි මෙයා red කරලා තියෙනවා. එකක් තමයි virtual memory ඕන වුණොත් එයා දන්නවා දැන් වැඩේ නාන්න වෙනවා කියලා. අනිත් අතට එයා දන්නවා මේකට අප්ඩේට් එකක් එහෙම આવත් එයා ටක් ගාලා ටෙම්පරරි එකට ගහනවා. බෑකප් ගහනවා. බෑකප් ගහනකොට ඊටමදි වෙනවා. ඒකයි මේ red කරලා කියන්නේ. දැන් හොඳට දැක්කේ මේක. සාමාන්‍ය මේක red කියන්නේ මම clean up කරන්න ඕනේ දැන්. clean up කළා මේවා ආයි නිල් පාට කරලා දෙන්න ඕන. එහෙම නැත්නම් එයාට virtual memory ගන්නකොට ප්‍රශ්න වෙනවා. හරි. ඊළඟට update එකක් major update එක දැන් Windows 11 එකට අපි දත මැදගෙන ඉන්නේ නේද? Windows 11 එක එයි කියලා කොයි වෙලාවක හරි Windows 11 එක එනකොට අනිවාර්යෙන් මෙයාට සෑහෙන ඉඩ ප්‍රමාණයක් දීලා තියෙන්න ඕනේ එයාට backup කරගන්න. නැත්නම් එයාට backup කරගන්න ඉන්න නැතුව එයා update එක ගහන්න නැතුව ඉන්නවා. හරි. අනිත් අර තමයි මෙයාට virtual memory එකට ඉඩ දෙන්න ඕන. හරි. Right. So I hope you got the answer. Okay. Right. So now how do we convert this? How do we convert the logical address into the physical address? So there's a way to do that. Right. Your operating system will refer to the logical address. Right. What මතකනේ අපි කතා කරා අපි මේ instruction format එක මේ instruction එකේ තියෙන බලමු instruction එක ඊට පස්සේ say මේවා address formatting කිව්වා මෙතන දෙන්න පුළුවන් memory address එකක් වෙන්න පුළුවන් කිව්වා registry address එකක් වෙන්න පුළුවන් කිව්වා immediate වෙන්න පුළුවන් කිව්වා ඒ කියන්නේ value එක registry address එක memory address එකක් ඔය memory address එකක් නම් ඔය memory address එක විදිහට උතන තියෙන්නේ මොකද්ද logical address එක තමයි තියාගන්න හරි ඇත්තටම computer system ඉගෙන ගත්තට පස්සේ තමයි හරියටම software එකට run වෙන්නේ කොහොමද කියලා දන්නේ හරි මේ logical address එකක් තමයි යාට තියෙන්නේ හැම program එකක්ම ඒ logical address වලින් තමයි වැඩේ කරන්නේ logical address වලින් තමයි වැඩේ කරන්නේ so now that logical address has to be converted to the relevant physical address right relevant physical address so how do we do that right how do we do that I told you that here you have the pages in the physical memory you have the frames and which page is connected to which frame is there in our page table okay in our page table but this is happening at page level not individual address we are not directly converting one address to the other address your page table doesn't have one-to-one address mapping this physical address is this logical address is this physical this address is this physical no there's no such thing because if you do that right your page table is going to take exactly the same amount of your memory 4GB තියෙනකොට ඔයාගේ memory එකකින් සෑහෙන කොටසක් යන page table එකට right one to one map කරනවා so therefore it's not efficient so therefore it is doing only page to frame mapping by doing some calculations your operating system can calculate exactly what is this logical address to physical address right but we are not keeping one by one we are just keeping page to frame table only okay right? So this is how it happens. Now assume that you know that your addresses are in binary. Say we have address, logical address like this, right? And your physical address will be, now it has to generate the physical address. Okay, it has generated physical address. This right hand portion is the same. Say it is something like, from here we say if this is 0011 in physical address also this is 0011, right? You can see this is also D, this is also D. So that means this portion is not changed. Only change is this portion is changed to this portion, something else, 10110001, right? So your physical address, sorry, your logical address has two portions. Your physical address also has two portions, and in both addresses this right hand portion is the same. Okay? This right hand portion is the same. Okay, right? So therefore it will simply copy these bits from here to here when it generates in the physical address. These set of bits will be simply copied. Now it has to find what are the corresponding bits for this portion. That is where it used the page table. Okay, so it will check what is this number. If that for that number, what is the frame number? Say page number is 14, it will come to the 14. Say the frame number says 4, and now it will be 4 here. This is bit pattern for 14 because this is 14. This says say 4, and now this is bit pattern for 4. Good. So this one. Okay. So therefore this portion will be the same. Only this portion to this portion mapping is done. It is done through the page table. It is done through the page table. Okay. Right. So these are very important. These portions are the same. How to map P to F? By page table, using the page table. Okay. Right. So this D part is called the offset. This D part is called the offset. So why offset is the same? Offset කියන්නේ මොකක් හරි තැනක ඉඳලා කොච්චරක් එහාට යන්න ඕන. මේ the page size, this is our page, and here you have the frame. Your page size and frame size is the same. So therefore in your page, if this memory address is the 10th one in your this is your page, in your frame also it will be your 10th one. So therefore this offset is not going to be changed. So that is why we just copy this portion to this portion, right? Only thing is this page number to frame number we want to find in that frame, right? In that frame this offset is not going to be changed. So that is why we just copy this portion to this portion. Okay, right? So everything has a reason. නිකම් මේක copy කරා කියලා කියන්නේ නැහැ නේද? හේතුවක් ඇතුව තමයි මේ කතන්දරේ කරගෙන යන්නේ. Right? So I hope you understand it, can understand it. Still if you don't understand, you can ask. දැන් මට හොත් සාමාන්‍ය තේරෙලා නැත්නම් මම බය නැතුව question අහන්න කියන්නේ. දැන් මටත් වැඩි තේරෙන්නේ නැති කොටස් වල මම නිතර කියන්නේ question අහන්න කියලා. දැන් මම මොකටද ඊළඟ පරිප්පු ගන්න නේද? So I am confident about this area, okay? Because this is pure logic, okay? Right, because you never know, they have not asked this direct page translation yet, because they are asking some advanced things like caching. Caching තේරුම් ගන්න කලින් මේ හරිය තේරුම් ගන්න ඕන. සමහරවිට ඕගොල්ලන්ගේ අවුරුද්දේ මේ හරිය question එකක් දෙන්න පුළුවන්. මොකද මේ පාර තමයි අන්තිම වතාව නේද? computer system 2 තියෙන අන්තිම වතාව. ඒගොල්ලෝ එච්චර අමාරු ගන්න එකක් නැහැ paper එක. හරි, paper එක අමාරු කරන්නේ නැතුව ඒගොල්ලන්ට කියන්න පුළුවන්. හරි, මේක A level ICT වලත් තියෙනවානේ මේ හරිය. අපි මේ හරියම question එකක් දෙන්නම් කියලා කෙලින්ම මේ වගේ එකක් දෙන්න ඉඩ තියෙනවා ඔයගොල්ලන්ට. හරි. අර caching වගේ වට නොගින්. Right. So this is an example. Right? So this is an example. So I am referring to the note that I have shared in the this one. Okay, I will upload it to the Google Classroom. Right. So this is, assume that this is your logical address. I will zoom it. Right. So this is your logical address, incoming logical address. Okay, incoming logical address. What the logical address එකක් program එකේ අර code වල තියෙන්නේ. Code වල තියෙන logical address. Now your operating system know where this division කැඩෙන්නේ කොතනද කියලා එයා දන්නවා. හරි, logical address එකේ left portion එකයි right portion එකයි කැඩෙන තැන දන්නවා. හරි. right, මේක විදිහට නම් එයා අරන් තියෙනවා bit කීයද 1 2 3 4 5 6 ඔන්න ඔතන ගණන් අරන් තියෙනවා. හරි, ඔතන අරන් තියෙනවා කියන්නේ මෙන්න මේක. now you can see that 0 0 0 0 0 0 blah 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 1 0 0 0 0 0 0 1 0 0 අර වෙන මේ ටිකේ වෙනසක් නැත. ඒක 1 to 1 copy වෙනවා. 1 to 1 copy and your operating system know where this boundary. Okay, because this is the offset. අර page එකේ නැත්නම් frame එකේ key වෙනි entry එකද කියන එක තමයි තියෙන්නේ. key වෙනි entry එකද 10 වෙනි එකද 12 වෙනි එකද හරි 600 වෙනි එකද කියන එක තමයි තියෙන්නේ. ඒක page එකේ 10 වෙනි එක නම් frame එකේ 10 වෙනි එක වෙන්න ඕනේ. ඒකයි මේක copy වුනේ කෙලින්. හරි. Right, now we want to translate your frame to the page, and I told you that we have bigger logical memory, smaller physical memory. නේද? එහෙනම් අනිවාර්යෙන් මෙතන bit 4ක් නම් මෙතන bit 3ක් වගේ වෙන්න ඕන. 4ට අඩු වෙන්න ඕන. ඇයි? address මේ දින addresses නේ. එයාගේ address එක පොඩි වෙන්න ඕන. ඇයි මේ පැත්ත පොඩි? මේ පැත්ත පොඩි. මේ පැත්ත ලොකුයි. එහෙනම් අනිවාර්යෙන් මෙයා bit 4ක් නම් මෙයා bit 4ට අඩු වෙන්න ඕන. හරි? කොහොමද මේක කරන්නේ? Now this is your page table. Page table. You find out what is this number. Say 0010 is 2. Right? 0010 කියන්නේ මොකක්ද? 10 පාදෙන්. මේක 10 පාදෙන් දාලා තියෙන්නේ. නැත්නම් මෙන්න 00 මේ විදිහට යන්නත් තියුණා. So 2. So you go to the second entry. And your second entry says, first check whether it's a valid or invalid. මේ තියෙන valid invalid bit එක නැත්නම් present absent bit එක. It says 1. 1 කියන්නේ හරි. මෙයා ඉන්නවා. මෙයා අපේ physical memory එකේ ඉන්න කෙනෙක්. මෙයාගේ page එක, මෙයාගේ frame එක තියෙනවා අර. එහෙනම් valid නම් තමයි මේක බලන්න. valid. So therefore now we have to copy, instead of 0010 we have to copy 110. මෙතන තියෙන entry එක තමයි copy කරන්නේ. ඔන්න හම්බුණා physical address එක. Okay. That's it. If this is 0101 නම් එතකොට යනවන කීයද 101 කියන්නේ 1 2 1 2 4 5 මෙන්න මෙතනට යන්න ඕනේ. එහෙනම් මම copy කරන්න ඕන 011 කියලා මෙතන. හරි. හැබැයි හදිසියවත් මෙතන තියෙන 0 නම් that means it is not in your physical memory. Then you have to wait until that page is loaded from virtual memory to the physical memory. Once it is loaded to the physical memory, your operating system is going to update the page table. And now again you can do this. And then what? එතකොට මේක 0 තිවිච් එක න 1 වෙලා තියෙයි. එතකොට දැන් ඔයාලට ආයිමත් physical memory එක calculate කරන්න පුළුවන්. මොකද physical memory එකෙන් තමයි data එක අරන් එන්න ඕන. වෙන කොහෙවත් අරන් එන්න බෑ. virtual memory එකෙන් data අරන් එන්න බෑ. hard disk එකෙන් data අරන් එන්නේ නැහැ. memory එකට අරගෙන තමයි I access කරන්නේ. ඔන්න ඕකයි වෙන්නේ. හරි. ඔන්න ඕකයි වෙන්නේ. I hope you can understand it. Okay. මේක හොඳ ගණන් දෙකක් තියෙනවා. එකක් past papers A level past paper එකක තියෙන question එකකුත් තියෙනවා. මේ කැමති අය පොඩ්ඩක් බලා ගන්න. මේ වගේ ගානක් දෙන්න ඉඩ තියෙනවා. හොඳට ඉඩ තියෙනවා ඔයගොල්ලන්ට. exam එක ලේසි කරන්න කියලා ඉදාගෙන දෙන්න ඉඩ තියෙනවා. හරි. තවත් ටිකක්. හරි අපි ඔන්න එක කරමු. આવොත් එහෙම නේද? right. If right, exercise මේක exercise එකක් වුණා මේ question එක දීලා තියෙන්නේ අර ගාන හදාගෙන යන විදියට. හරි. right. Assume that logical address space is 4 GB. Okay, logical address space එක 4 GB කියලා හිතන්න. හරි? අපි හිතමු එහෙනම්. හිතන්න දානවා නෑ. 4 GB. මම මේ පැත්තෙන් logical මේ පැත්ත physical ලා. This is 4 GB. Physical address space is 64 MB. පොඩි memory එකක් පුදින්න. එයා සුළු කරන් ලේසි වෙන්න. Page size is 4 kilobyte. මේ වගේ එක page එකක් 4 kilobytes ලු. ඒ වගේ pages තමයි මේකේ තියෙන්නේ. මේවත් විතර 4 kilobyte. This is a page, this is a frame. ඒ frame එකට page එකක් කියලා set වෙන්න පුළුවන්. හරි? Memory is byte addressable. ඒ කියන්නේ හැම byte එකකටම address එක ගන්න තියෙනවලු. හරි. Calculate number of pages. හරි, number of pages. දැන් මේ තියෙන experience එක පාවිච්චි කරලා ඔයාලට දෙනවා ඊට පස්සේ තනියෙන් හදන්න මේ question එක. හරි. මේ තියෙන ගාන බෙදලා හදන්න තියෙනවා. හරි. මේක ඊට වඩා පොඩ්ඩක් වෙනස් වෙයි. හරි. So number of pages. What is the number of pages? So we have pages are here, frames are here. මතකනේ? pages තියෙන මේ පැත්තේ, frames තියෙන මේ පැත්තේ. Page size is same as frame size. So number of pages is altogether logical address space is 4 GB. One page is 4 kilobyte. ඉතින් මේක පොඩි ළමෙක්ට හදලා දෙන්නේ 4 GB divided by 4 kilobyte. දැන් හරියට ගිගා කිලෝ එක වැඩ කරන්න ඕන. 4 into kilo giga is 2 to the power kilo 2 to the power 10 kilo mega giga 10 20 30. 4 kilobyte can 2 to the power 10. So that means 2 to the power 20 bytes for 1 megabyte. Megabyte එකක්. megabyte එකක් කියලා කියන්න බෑනේ. Number of pages නේ අහන්නේ. Number of pages එනවා කොච්චරද? 2 to the power 20. يعني 1024 වැඩි කිරීම 1024 page තියෙනවා. හරි 1024 into 1024 pages are there. 2 to the power 20 pages will be there. Right? So number of pages is 2 to the power 20. හරි ඒක අගහරි කරලා තියෙන්නේ. තේරුණානේ? Right. What is the next question? Number of frames. Number of frames කියන්නේ කීයද? ඔක්කොම 64 megabyte. 64 megabyte බෙදන්න ඕන කීයද? 4 kilobyte වලින්. හරි මේක 4 kilobyte නම් මෙයාත් 4 kilobyte. අපේ page size frame size සමානයි. So 64 megabyte mega karna 2 to the power 20 4 kilobytes 2 to the power 10. So here 2 to the power 10 then 2 to the power 4 and 2 to the power 14 2 to the power 14 frames are there. Sorry 2 to the power 20 pages are there. 2 to the power 14 frames are there. So number of frames is 2 to the power 14. Number of frames but that is answer 2 to the power 14. Right. Number of entries in the page table. page table එකේ entries කීයක් තියෙනවද කියලා අහනවා. page table එකේ හැම page එකකටම entry එක ගන්න තියෙනවා නේද? සමහර ඒවා invalid කියලා ඇති. හැබැයි හැම page එකකටම entry එක ගන්න තියෙනවා. නිකන් number of entries in page table is 2 to the power 20. Right? Number of entries in page table is 2 to the power 20. Right. සමහර වෙලාවට උත්තර ලියන්න අමතක වුණා මොකද ඊළඟ හරිය තමයි වැඩේ යන්නේ මොකද වැඩි attention දියලා නැහැ මේ කොටසට. Right. So size of the page table size of page table කියන්නේ ඒකම තමයි number of entries මම ආයෙත් දෙපාරක් අහලා තියෙනවා හරි. Right. දැන් අහනවා physical address format එකයි logical address format එකයි කියන්නලු. දැන් ඔන්න හොඳට කල්පනා කරන්න ඕන. Right. So now we have 4 GB. Right. So let's start with the logical address. Okay. Now it says byte addressable. Every byte has a right because memory is byte addressable. Every byte has a memory location. Right. Every byte has a memory location. And your logical address space is 4 GB. Right. Your logical address space is 4 GB and every byte has a address. Therefore, how many addresses will be there? 4 GB divided by 1 byte. Right? 4 gigabytes divided by, because 4 GB memory is there, every byte has address. So therefore, you get 4 GB divided by 1 number of addresses. 4 GB is 2 to the power kilo mega giga 2 to the power 30. So that means 2 to the power 32 addresses will be there. How addresses kya thi na? 2 to the power 32 addresses thi. Right. So if you have 2 to the power 32 addresses, how many bits are needed to create address? Me address එකක් හදාගන්න bit කීයක් ඕනද? If you have 2 to the power 32, if you have 2 addresses, I need 1 bit. 4 addresses, I need 2 bit. 8 addresses, I need 3 bits because 0, 0, 0 to 1, 1, 1. If you have 2 to the power 32 bit addresses, you need 32 bit. Logic එක ගන්න ඉන්නේ ඉතින්. හොඳට මතක තියාගන්න මේක all A level ICT question එකක් මේ කරන්නේ. මේ A level ICT note එක. ඔයගොල්ලෝ උරතල් වෙන්න එපා ඒක හන්ද හරි. පොඩි උන් මේක කරන්නේ 18 එමු. ඔයගොල්ලෝ දැන් වයසට යනකොට හැබැයි ඔළුව එන්නේ නැ සවුත් වෙනවා හැබැයි සමහරුන්ගේ අපේ නම් ඔළුව තාම සවුත් වෙලා නැහැ. මේ වැඩ කරන හන්දමද මන් දන්නේ නැහැ. right සාමාන්‍යයෙන් ගොඩක් අය මේක හොඳටම පේන එකක්. හරි A level A level පන්තින ළමයින්ට වඩා මම දැන් ඔය ඔක්කොම කරනවානේ A level කරනවා PT BIT කරනවානේ. බොහෝ විට A level පන්තින ළමයින්ගේ ඔළුව sharp. හැබැයි BIT first year එනකොට ඔළුව කුරෝලු. මම දන්නේ ඇයි එහෙම වෙන්නේ කියලා. ඒ අවුරුදු දෙකට මොලේ කිවිලද දන්නේ නැහැ. Right. So we need 32 bit now. Right. Now we know that page our logical address need 32 bit. Right. And we know that it has two portions: the page number and the page offset. Right. Page number and the page offset. And now we know how many pages are there. එහෙනම් අපි දන්නවා page number එකට bit කීයක් යනවද කියලා. ඒ ඉතින් pages ගන්න හොයාගත්ත ඒකනේ. මෙතන තියෙන page number එක. And here it is a page offset. Right. So page offset එකට යන bit ගණන් දැන් අපිට හොයාගන්න පුළුවන්. ඒ page එක size එක දන්නවනේ. page එක size එක කීයද හොයාගත්තේ? page එක size එක ආවේ කීයද? අපිට දෙන්න තියෙන 4 kilobytes නේ. 4 kilobytes තියනවා නම් එක byte එකකට address එක හැම byte එකක්ම තමයි address එකකුත් තියනවා නම් නේද? byte address බලන්නේ. අපි 4 kilobyte කියන එක byte කරමු ඉස්සෙල්ලා. 4 kilobyte කියන byte කරාම 4 into 2 to the power 10. So that means my page size is 2 to the power 12 bytes. මගේ page එකේ byte 212ක් තියෙනවා. හරි. ඒ කියන්නේ මගේ page එකක මේ page එක නැත්නම් frame එක right one page has 2 to the power 12 bytes. Right? 2 to the power 12 bytes. And each location can hold 1 byte. So therefore, how many data entries are there? 2 to the power 12 තියෙනවා. Right? Make it addresses 2 to the power 12 තියෙනවා. Because every byte, one location can have only one byte. So if you have 2 to the power 12 data and each data is 1 byte, how many bits are needed for offset? 12 bits. Okay. Offset එකට bit 12ක් ඕන දැන්. ඇයි? 2 to the power 12 entries in a page එකක් ඇතුලේ. Now we are done. So altogether 32 bit. For the page offset we need 12 bits. Page offset එකට bit 12ක් එනවා. එහෙනම් මෙයාට යනවා මෙයාට කීයක් ඉතුරුනද? මෙයාට 20ක් හම්බ වෙනවා. page number එකට 20ක් තියෙනවා. page number එකට 20ක් එන්න ඕන කොහොමද අපිට මෙතනත් තාම දෙකේ 20ක් කියලා නේද? pages දෙකේ 20ක් තියෙනවා කියලා. pages දෙකේ 20ක් තියෙනවා. මේ පැත්තෙන් ගත්තත් 20ක් එනවා. දැක්කද? මේ පැත්ත මේ කරගෙන ආව 30ක් එනවා කියලා එනවා. මෙහෙන් අරගෙන අඩු කරාමත් එන්න ඕන. මොකද 32යි කියලා යදියා තියෙන එක හරියන විදියට. So now we know that this is 20, right? And this is 12. This is 12. මෙයා 12 හන්ද මෙයා 12. මෙයා 20යි. මොකද pages 20ක් තියෙනවා. 2 to the power 20 තියෙනවා. මම දැන් ටික ටික format එක හදාගෙන ඉන්නේ ආ. Right. Now this is 12 bit. Right? This is a page එක. ඒ හැම එකෙම 1 byte තියෙනවා. ඒ page offset එකට ඒකයි මේ 12 කියන එක ආවේ. හරි? දැන් physical memory එක size පැත්තෙන් calculate කරන් වෙලා හොයාගන්න පුළුවන් මොකද්ද? එයාගේ මේක කොහොමද 12 වෙන්න බෑ? offset එක වෙනස් වෙන්න බෑනේ. ඒක මෙයා 12යි නම් මෙයා 12යි නම් මෙයා 12 වෙන්න ඕන. මෙයා 12 වෙන්න ඕන. අපි කියන්නේ ඒ offset එක වෙනස් වෙන්න බෑනේ. එකම size නේ. අනිත් පැත්තෙන් ඔයාලට number of pages කියන හොයාගත්තා නේද? ඒක පාවිච්චි කරලා ඔයාලට කියන්න පුළුවන්. sorry number of frames වලින් හොයාගන්න පුළුවන්. මෙතනට bit කීයක් යනවාද කියලා. මේකට ඒකක් හරි. ඔය උදාහරණ කියදී. මේ පැත්තේ format එකේ bit කීයක් තියෙනවද? මේ පැත්තේ bit කීයක් තියෙනවද? ඒක කොතනින්ද කැඩෙන්නේ? හරි? Right. So I hope you can understand it. Okay? Right. On the note එක ඉවරයි. O level ICT OS note එක. හරි? Right. Now we are coming back to our one. Right. So we'll take a small break. After the break, we'll do this particular question. Okay, this particular question. So now it's 9:10. We'll be starting at 9:25. So this is 2019 question 1. Okay, question 1. Okay, so let's read the question. A computer system has CPU which has 256 numbers of 64-bit general purpose registries, right? So there are general purpose registries, that is where you keep your data inside your processor. So there are 256 number of registries, 256. Okay, 64-bit general purpose, so that means each location you can keep 64-bit. Anyway, we are doing this, right? So 64-bit, each location 64-bit. 64-bit means in byte 6 byte. Okay, 6 byte, 6 byte, and each location can keep 6 byte, and there are 256 of like that, right? This is registries. Okay, it has 48-bit virtual addresses, right? So 48-bit virtual addresses, right? So that is needed later. Okay, so the first question is, what is the total size of the register memory in bytes? That is very easy, right? That is very easy. What is the total size of register memory in bytes? So we have one location, so that is only first portion is needed. one location it says 64 bit or 6 byte, and there are 256 registries. One registry can keep 6 byte or 64 bit. Okay, and there are 256 of like that. So therefore, what is the total capacity? 256 into 6 byte. Right? 256 into 6 byte. So 6 byte එක කොහොමද මේ 64 8ෙන් බෙදලා. හරි 64 8ෙන් බෙදුවා ඒක 256ෙන් වැඩි කරලා අපිට byte වලින් දෙන්න ඕන. Right? So the final answer is 2048 byte. Right? 2048 byte. So there are 256 locations, registry locations. Each location you can keep 6 byte or 64 bit. Okay. Right. So let's do the second one. මේක නම් උත්තරේ පොඩි වැරද්දක් තියෙනවා මට පේන විදියට. What fraction of virtual memory pages can be there in the physical memory at any given time? Right. So දැන් අපි ඉදිරියට කියවන්න ඕන. පළවෙනි කොටස හරි. The system has 2 GB RAM. System එක තියෙනවා මොකද්ද? Physical memory එක. RAM කියන්නේ physical memory එක 2 GB. So this is your physical memory. It has 2 GB. 2 GB means 2 into 2 to the power 30 byte. Right? Byte. Right? 2 GB memory. 2 GB RAM. Virtual memory page. Right? Virtual memory page with 4 megabyte page with 4 megabyte pages. Virtual memory එක. හරි? නැත්නම් ඔයාගේ logical memory එක page එකක් 4 megabyte ලු. ඒ කියන්නේ page size එක. මෙතන virtual memory කියන්නේ logical memory එක. මම කිව්ව logical memory එකට virtual memory කියලා කියනවා කියලා සමහරවල්. හරි? And external cache is 1 megabyte. cache එකක් තියනවලු 1 megabyte. ඒක අපිට එච්චර ගණන් ගන්න දෙයක් නැහැ. ඒක අනවශ්‍ය දෙයක් අපිට දීලා තියෙනවා. හරි? මොකද cache එකේ තියෙන වෙන වැඩ වලටනේ. සමහරට question එක වල අනවශ්‍ය දේවල් කියනවා. buy කරන්න. The system disk size is 100 gigabyte. System disk එක නැත්නම් වගේ system disk එකේ තියෙනවලු gigabyte 100ක්. right. ඔච්චර දිලා තියෙනවා. right. What fraction of virtual memory pages can be there in physical memory at any given time? At any given time, what fraction of virtual memory pages can be there in the physical memory? මේ virtual memory pages කීයක් physical memory එකේ ඉන්න පුළුවන්ද කියලා අහන්න. ඉස්සෙල්ලා බලන්න ඕන virtual memory page එකක size එක කීයද? 4 megabytes. ඒක දිලා තියෙනවනේ දැන්. හරි. Virtual memory page with 4 megabytes. So you can virtual memory එකේ එක page එකක් 4 megabytes. Equal 4 into 2 to the power 20 byte. Right, 2 to the power 20 byte. Right, 2 to the power 20 byte. මේ වගේ pages virtual memory pages කීයක් physical memory එකේ ඉන්න පුළුවන් දාන එක වෙලාවක. එහෙනම් ඒක කරන්නේ කොහොමද? The total physical memory. So you have to divide total physical memory by the virtual memory page size, because here also the same page size. Right? This is 4 megabyte. This is also 4. So therefore, this is 2 GB. 2 GB means 2 into 2 to the power 30. Right? 2 into 2 to the power 30 divided by 4 into 2 to the power 20. So sulu karot there's 1 2 2 here 2 to the power 10 and sorry 2 to the power 30 minus 2 to the power 20 is 2 to the power 10, right? And then there's one more, that is 2 to the power 9 men now. 2 to the power 9, right? But the answer they have given is 2 to the power minus 17. That I have no idea why, right? So it has to be 2 to the power 9. 10 to the power එකක් ආවේ කොහෙන්ද කියලා මම නම් දන්නේ නැහැ. හරි? So usually you don't have to go for 10 to the power. Right? So the physical memory, in the physical memory, right? So one page is 4 megabyte. So therefore altogether 2 GB, 2 into 2 to the power 30 divided by 4 into 2 to the power 20. And 4 megabyte. So answer must have been 2 to the power 9. 2 to the power 9 pages තියෙන්න පුළුවන්. That is 512, right? 512 pages තියෙන්න පුළුවන්. Right? So answer should have been 512 pages. 512. Okay. I don't know why they have given something else. Okay. Right. Third question. How many CPU words can occupy a page block? Now your page block is how much? 4 megabyte. So they have given it 4 megabyte. Right. So your entire page is 4 megabyte. Okay. Then how many CPU words can occupy page block? So we have 4 megabyte. Then what is the value of one entry? Have they given that? So one entry must be fit into your registry, right? So your memory, one entry of your memory must fit into your registry, right? So that is the logic. So therefore now we know that registry width is 6 byte or 64 bit. So therefore this one must also be 6 byte because your registry width is 6 byte. So therefore your page width must also be 6 byte. 6 byte. Nah. 64 divided by 8 is 8 byte. Sorry, yeah. Make 6 name here. 8 byte. 64 divided by 8 is 8 byte. Okay. Yeah, so that is 8 byte. මෙතනත් ඒ වැඩි වුණාද? වන්නේ නැහනේ. No, මෙතන total නෑ. හරි. Right, 8 byte. So therefore, how many CPU words will take up the page? Your page is 4 into 2 to the power 20. Each entry can be 8 byte. 8 byte. And this is 4 megabytes. 4 into 2 to the power 20. So therefore, how many entries will be there? 4 into 2 to the power 20 divided by 8. So that is 2 to the power 19. So that answer is correct. Okay, 2 to the power 19. So that is how you do it. Right? Page translation එකක් ගැන අහලා නැහැ. හරි, memory address translation එකක් ගැන අහලා නැහැ. Just normal question, right? So shall we do this one also? Right, we can do this one also, right? Right, because we have done the address. We did the address format as well as we did the memory addressing modes, direct, indirect, right? And also we did the immediate, direct, indirect, and displacement. Okay, right? So therefore we can do the B part as well. So this portion we can do now. Consider the following RISC instruction contained in a thread that is running on a processor. Right? It's a thread running on a processor, and this is assembly code. This is assembly code. So these kind of assembly codes are the code that is run, decoded and executed by your processor and run. Right. So what are the instructions? Load R1 200 R0. So these are pseudo assembly code. So right, pseudo assembly code. So therefore they will give you what does it mean? Load the content of memory location 200 plus R0. That means displacement, address mode. So whatever the value in the registry 0, add 200 to that. Right, so then that in that memory address, whatever the value in that memory address, load to the registry 1. Right, load the content of memory location 200 plus R0 to registry R1. So that is your first instruction. Right. Second instruction is subtract R3, R2, R1. So what does it mean? They have given subtract R2 from R1 and save it to R3. Right. So you have to send the R2 and R3 to the ALU and ask it to subtract. Then the value you have to put it into the registry 3. So that is your second instruction. Third instruction, store 300 R0 R3. store the R3, whatever the value in register 3, at memory location 300 plus R3, again index or the base addressing mode. Right? Add the value in R0, 300 to R0, to that memory location you have to write the value in register 3. Right? So that is a store operation. Right. Those are the 3 instructions in the program. Right. Now the question. If memory referencing instruction takes 3 clock cycles, so now it is saying that if you are accessing the memory, it takes 3 clock cycles, right? 3 clock cycles, and arithmetic instruction takes 1 clock cycle, right? So now the examiner has given you. So usually that is correct. Why? When you want to access memory, you have to go to the memory. It is not right. It usually takes more clock cycles, but in arithmetic instructions happening inside the processor. So if something happens inside the processor, you need lesser number of clock cycles. But if you have to go to the memory, it is always taking more time. So therefore, it says the question says memory references take 3 clock cycles. Arithmetic operations take only 1 clock cycle. Right. So what is the average CPI? Cycles per instruction. How many cycles take for instruction on average? For the above piece of code, if the code is executed on non-pipeline processor, assume that there is no pipelining, this is executed one after the other. Okay. Right. Now, now first you have to see how many clock cycles it will take. Of course, cycles per instruction means what? Number of clock cycles divided by number of instructions. Right? Say it takes 100 cycles to execute 10 instructions. Then CPI is 10. Say it takes 100 cycles to execute 20 instructions. So the CPI is 100 divided by 25. Okay, 5. Right, so therefore we have to find out how many clock cycles we need for this program and how many instructions are there in this program. Obviously there are 3 instructions, right? There are only 3 instructions, first one, second one, third one. So therefore the number of instruction is 3. Then what is the total number of clock cycles we need? It says 3 clock cycle for memory referencing. So there are 2 memory referencing instructions. Load, you read from the memory to the register 1, and store, you write your register 3 into this particular memory address. Right? So therefore 2 memory referencing instructions and 1 arithmetic instruction. So memory referencing instruction take 3. There are 2 such things. Therefore 6 clock cycles. And 1 arithmetic operation. For that you need 1 clock cycle. That means all together we need 7 clock cycles. Right? 7 clock cycles. And we need 7 clock cycles, and we are in those 7 clock cycles we are executing 3 instructions. So therefore cycles per instruction is number of cycles divided by number of instructions. Number of cycles 7. Number of instructions 3, therefore CPI is 7 divided by 3, 2.3. 2.3. Okay, so that is how you do it. So if you have any questions, you need to ask. Right, so let's move on to the second part. If R0 equals 0 and R2 equal 20. Now they are talking about the registries, right? Say R0, register 0 is having 0. Register 2 is having 20. And the content of the memory location 200 is 40. So memory location 200 is having 40. Right? What would be the content of the memory location 300? What is the value of memory location 300 after executing the code? Right, after executing the code. Right, so what is the code? What is the code? Right, first I will delete this. So this is the current situation. Right? This current situation. Right? R0 has 0, registry 2 has 20, and memory location 200 has 40. Memory location 200 has 40. Right, that's it. Okay, I will delete this also. Right, now it's going to execute. After execution of the code, what is the first code block says? First instruction says load R1 200 R0. That means whatever the value in registry 0 at 200, then in that memory location load that value into the registry 1. Right, so what is value in R0? 0. So therefore 0 plus 200 is 200. So that means we have to load the value in memory location 200 to the registry 1. What is the value in memory location 200? 40. So therefore this 40 is loaded to registry 1. Right, 40 is loaded to registry 1. Right, so this 40 is loaded to registry 1. So therefore your registry 1 is now having 40. That is your instruction 1 after execution of the instruction 1. Okay, right. So what is the second instruction? Subtract R3 R2 R1. So it explains subtract R2 from R1 and write the value to the registry 3. So that means we have to do R2 from R1, that is R1 minus R2 we have to calculate. Right, R1 minus R2. R1 minus R2 is R1 we have 40, R2 we have 20, 40 minus 20 is 20. Right, 40 minus 20 is 20. That we have to put it into R3, save onto R3. So that means we are going to save 20 into R3. R3 is now 20. Okay, another registry. Now what is the final statement? Store R0 300 R3. That means add the value in R0 to 3 at 300 to value in R0, and that location you put the value store the R, whatever the value in R3 you store into that location, and we know that R0 we have 0. That means basically we have to store the value in registry 3 into the memory location 300. Right, so to the memory location 300 we have to store the value in this R3. So therefore here it will be 20. That is your third instruction. Right, so now what is the final question? What would be the content of the memory location 300 after execution of the code? The value is, answer is 20. Right, so here the answer is wrong, obviously wrong, because the examiner has taken this as plus R3 equal R2 plus R1, but the question clearly says it is not R3 equal R, it's not addition, it is a subtraction. So therefore examiner has messed it by adding R2 and R1. So he has added 40 and 20 and 60. Right, so that is the issue. So it's not 60, it is 20, because we have to do the subtraction. So that is so therefore your R3 must be having 20, not 60. So okay, may I add karna kiyala gattanta metanta 60 dala tiyenne. So this answer is wrong. Answer is 20. Okay, answer must be 20. Right, so third one. So if you have any questions you need to ask. Suppose now the above code is to be executed on typical 5-stage RISC pipelining. So that is what we discussed, right? 5-stage pipelining. Instruction fetch, instruction decode, execute, memory access, write back. Draw space-time diagram to show the overlap execution of the 3 instruction, state any assumptions. Right? State any assumptions. So what is the normal pipeline process? We start the execution of the second instruction when the first instruction is in the second stage. Right? We start the execution of the third instruction when the first instruction in the second stage and the second instruction is in the first instruction in the third stage and the second instruction in the second stage. Okay, right? It's very easy, right? So this is IFID EXMEM WB, second one IFID, third one IFID. So when this is in the decoder, this has started. When this is in the execution and this is in the decoder, the third one has started, right? So that is the normal thing. That is normal thing. Okay. So you have to write down any assumptions. The assumptions you have to write. The assumption is no hazard happen. No pipeline hazard. Because if there's a pipeline hazard, sometimes you have to delay. You have to go for bubble. Assume that no pipeline hazard, then this is the happy scenario. This is happy scenario. Okay. So assume that there is no pipelining. Sorry, there is no hazard happening right now. So therefore, this is the answer. Okay. Right. So fourth one. If each stage take only one clock cycle, what is the cycles per instruction? So that means each stage take one cycle. That means for one instruction it takes 5 cycles. Okay. What is the CPI of the above code executing on pipeline processor if the data hazards are assumed to be eliminated? Right. So assume that there is no data hazards. Okay. Then what is the CPI? Right. Now we know that when we go for pipelining, if we have 5 stages, we can increase our speed up our processing by 5 times. Of course, when you have so many instructions, okay. Otherwise, because at the starting point there is delays. When you are stopping, there are delays. But if you have thousands of instructions, it's roughly getting 5. If it is 5 stage, 5 times. Otherwise, you have to use that formula that we discussed. Okay, remember we discussed the formula. We have to use that. But this is we have only 3 instructions. So when we have only 3 instructions, still actual pipelining hasn't started yet properly. Right, properly. Right. So therefore, you don't see much of an improvement yet, because you can see that there are how many. So we can say that this is done only after this. Only after this. By the time how many clock cycles are needed? 1, 2, 3, 4, 5, 6, 7. 7 clock cycles. Okay. 7 clock cycles. 7 cycles need to execute 3 instructions, right? 3 instructions. So that means cycles per instruction, 7 cycles for 3 instructions. So the answer is 7 divided by 3. But in reality, right, in reality, this is just 3 instructions, right? So when you go for large number of instructions only, you will feel that. So therefore, usually we can say that because it is okay, so it has to be 7 cycles divided. 7 cycles divided by 3 instructions. Yeah, so it has to be 2 point. Why it is saying 1? Yeah, right. So we have 7 cycles because it says each stage take only 1 cycle, right? Each stage take only 1 cycle means 1 2 3 4 5 6 7 cycles, and we have done 3 items, 3 instructions. So ideally it should have been 2.33 something like that, but I don't know why it says CPI is 1 by implication, cycles per instructions. It says each stage take only 1 clock cycle. It is not saying that each instruction take 1 cycle, right? If each instruction take 1 cycle, this is roughly, yes, 1, right? Roughly 1. But it says each stage take only 1 cycle, right? I don't know. I don't know why they have taken it as 1. It looks like the answer must be 2.33, right? 2.33. But I don't know why they have taken it as 1, because it clearly say that each stage take 1 cycle means for this instruction itself you need 5 cycles. So then how do you say that cycles per instruction is 1? Right? Cycles per instruction is 1. But the reality is, if you have so many instructions, okay, so that means thousands of instructions, yes, then every cycle one instruction is finished, right? Every cycle one instruction is finished. In that case your CPI is getting closer and closer to 1. That is obvious, right? That is obvious, because now you can see that after some times every cycle one instruction is done. So therefore if it is big program, this is getting closer to 1. Right? But I think this one is asking for this program. What is the CPI of the above code? So therefore I don't like this answer at all. It says for the above code, right? Not for a big program in general, right? So therefore if you take only this code, I would definitely say send 7 cycles for 3 instructions. So therefore I would say 2.33. Right, rather than 1. So my answer is 2.33 CPI, right? 2.33. So my answer is 2.33 CPI. Okay. So I don't agree with this answer. Okay. So you can think about it. You can think about it. If you feel like no, you agree with the examiner, not with me, you can talk. You can talk. I'm always open. Okay. Right. So this is, I have conflict with the marking scheme answer. Okay. Right. Right. So that's it for that. Okay. Right. So we did full question from 2019 paper. Right. So let's now go through some of our notes as well. Now I hope now your confidence is bigger than last week, right? So this subject is all about your confidence. This is not something you can memorize, right? So you must build up that confidence day by day, okay, session by session, right? So let's move on to our note again. Okay, I have closed the note. Yes, I have closed the note. So today we didn't do much new things. Of course we did the process cycle, right? Some memory translation. Yeah, we did some new things as well, and we are using the cycles per instruction. Those things we did previously, right? Especially the CPI. And today we use the addressing modes, right? addressing modes in order to calculate those things. Okay. And also we use the general purpose register architecture. Your idea about this, right? Otherwise you don't get that questions, right? So when you read the question you don't get anything unless you know the general purpose register architecture and how the instructions are getting executed. Okay, and now we have done all these things. Again, don't worry too much about what are these things are doing, because in the exams they will give you the instruction and say this instruction is doing this, because these are pseudocode. So therefore don't worry too much about memorizing what is these instructions, right? So, and also don't get intimidated. You are they know. Right. And also last time we discussed about the RISC versus CISC architecture, remember? So always you get one question on RISC and CISC architecture and pipeline, right? One question, right? We did the 2020 paper question. So today we are going to do the 2019 question on RISC and CISC architecture, because we are parallelly doing questions as well as finishing topics. Okay, right? So now can you remember the difference between RISC and CISC? Right, so RISC computer, we have reduced instruction set computer, CISC complex instruction set computer, right? So in RISC, so can you create that RISC versus CISC chart? RISC, CISC. So we have small number of simple instructions are supported. Here CISC, large number of instructions. Why? Both simple and complex are supported. Large number of simple and complex instructions. And of course RISC architecture assume fixed size instructions, because we can go for that fixed size. This is variable size, because going for fixed size is a disadvantageous, because we have small instructions as well as very big instruction. So therefore we go for variable size. And because we use fixed size, we can go for pipelining, because pipelining expect that you have fixed length. Pipeline is possible. Here you can't, no pipelining. We have to optimize using other ways. Okay, and of course since we support only small number of simple instructions, our processor is simple, right? Simple processor. Here we need complex processors. So this is good enough for general computing, general purpose. But this is used when we have complicated things like database servers, web servers, etc. Right? Complex computing. Right? So very important. This is fixed size, therefore pipelining is possible. Variable size, therefore pipelining is not possible. Okay. Right? So those are important. And of course the 5-stage pipelining. And what are the hazards in the 5-stage pipelining? How to overcome data hazards, how to overcome structural hazards, how to overcome control hazards. So what are the two structural hazards we have? The registry hazard. How to overcome that? Your read is done in the second part, your write is done in the first part. So therefore it's not going to be conflicting, right? How to overcome the memory hazards? We have the instructions in one area, data in the other area, because the conflict is you access the instruction and also you access the data. So when you have two different areas and two different paths, that is also done. Then the data hazards we discuss, because the second instruction may need, right? So here you have the fixed size, therefore you can do the pipelining. Here you can't do the pipelining, you have to go for other things, okay? And of course the how to come up with those hazards, how to fix those hazards, the data hazards, how to fix those things. Remember we discussed about you can take from the buffer of the ALU rather than reading it from again registry, so that issue is fixed. That is how you overcome the data hazards. Okay, right. So now let's do the 2019 question. Okay, 2019 question on RISC and CISC computers. Okay. Right. So let's take. Right. In each of the following sentences, underline or circle the more suitable term from within the brackets to fill in the blanks. Okay. Right. In RISC, load store instruction set architecture, all instructions are of variable or constant length. We know that in RISC it is constant length or fixed size, right? So that is I already mentioned, right? So they must be fixed size, because otherwise you can do the pipelining. And also, since we have small set of simple instructions, going for fixed length is handy, advantages, okay, compared to CISC. Right, I forgot to mention one more point. In CISC architecture, right, in RISC architecture we have only registry addresses. Always first we load things to the registry, and addition and those things are always referred to the registry 1, registry 2, registry 3. Add the content in registry 1 and registry 2 and put it into registry 1. Say registry 2 and registry and put it into registry 1. Right, so we go for load the data to the registries, and do, when you are doing arithmetic and logic operations, we all refer to the registries. But when it comes to CISC architecture, right, so we can do something like this: add the value in registry 1 to value in memory 1 and put it into the registry 2. So that means here always we refer to the registry unless it is a load or store. But here, without loading to the registry, we can straight away access value in the memory as well in these instructions, right? So sometimes all memory, right, add the value in memory 1 and memory 2 and put it into registry 1, right? So then of course, now you can see again your instruction is getting complicated, because while you are executing, you have to access the memory also. Right, so that is also part of the CISC architecture, right? CISC architecture, they allow that, but in RISC architecture we always load things to the registry and then you do the calculations, and finally you write back to the memory. Okay, but here you can directly access memory in your normal instructions as well. Okay, right, so let's read up whose instructions compared to the sys or registry memory. So therefore sometimes here we call load store. We load to the registry, do the execution and store back to the memory. Here we say register memory because your instructions can refer to both registry and memory. So therefore sometimes without loading to the registry you can straight away take to the ALU and do the processing. Okay, so therefore another name we use for CISC is register memory. Another name for RISC is load store. Okay, right. So whose instructions are of variable length, right? In order that RISC CPU program counter can auto advance decoding of the instruction, right? So since this is fixed length, right, you know that your next instruction is in the next position. your next instruction is in the next position, your next instruction is in the next position. Why? Fixed length. Remember, usually after decoding only you know what is the next instruction after decoding. But in pipelining, even before decoding, we load the second one, which we can do because it's a fixed length. Even before decoding, we can load the next one, assuming that there is no control hazard. Right? Of course, if it is if else, now we are in trouble. I told you how to tackle that. But assuming no control hazards, we can always, you don't have to wait for decoding. You know that next instruction is the next location. So therefore, even before decoding, we can increment the program counter. But of course, after execution, if you find that it is a if else situation where it is becoming false rather than true, yes, we have to reload it. But in pipelining, we proactively load the next instruction. So therefore, yes, because fixed length, we know what is the next instruction in happy scenario, right? So therefore, in RISC architecture, especially when we are doing pipelining, we can auto advance prior to decoding, right? Prior to decoding, because it's a fixed length. We know that next instruction is the next memory location. Next instruction is the next memory location because it's a fixed length. But in CISC architecture, you have to decode, then only you know what is the next memory location, because variable length, right? Sometimes your instruction takes 2 memory locations, sometimes 1 location, sometimes even 3 locations, because your instructions are variable size. Okay. Right. So now with 2. In CISC architecture, which have small or large registry files. Now remember, in RISC, we always load to the registry and do the execution. In RISC, right? That is why we say load store. Load the value to the registry, execution. Arithmetic things are always taken from registry. Therefore, we need bigger registries, larger number of registries in RISC. But in CISC, we need lesser number of registries because we can directly take from memory to the ALU as well. So therefore, in RISC architecture, we need more registries. In CISC architecture, we can work with less registries. Okay, so therefore, in CISC architecture, which have a small register file, a procedure calls will make the operating system save the current registry file in the stack, whereas in RISC architecture with large registry files, because we have to load to registry and from registry only it's taken to the ALU. Okay. Current variable in the registry will not be saved on stack. That is additional thing. Okay. That is additional thing. Right. Third one. In RISC architecture can be efficiently instruction pipeline. So which one can be instruction pipeline? RISC. RISC can be pipeline because they have the fixed length. Since that is micro instructions can be grouped into independent blocks. Independent blocks means fixed size. In such a way that delay variation hazards among them can be minimized, right? So we know that when we have fixed length, we can give solutions to the hazards, because fixed length, it's predictable. We know exactly when the fetching happens, exactly when the decoding happens, exactly when the execution happens, exactly when the write back happens, right? Exactly when the memory read happens. So 5 stages. When they are fixed size, we know exactly when the things are happening. Then we can come up with solutions to those hazards. Okay, so we can give solutions to the hazards, right? We can minimize the hazards when it comes to RISC. But when it comes to CISC, minimizing hazards is extremely difficult because it's not fixed size, right? It's not fixed size, right? Fourth one, instruction. Right, pipelining superscaling allows processors to achieve a CPI of, right? So still we haven't done that. Superscaling, we haven't done that. We will be doing that. Actually, it's mentioned in your notes, but still we haven't touched that particular topic. So therefore, let's not do the fourth one. Okay. So the superscaling is in your note. Okay. Superscaling. Scaling. You can see superscaling, right? So it's there. Still we haven't discussed that. So when we come to discuss that, that is a multiprocessor. Multiprocessor, I haven't gone through the note your note yet. Okay. So therefore, let's not do the fourth one. Right. So these are again related to the. Okay. So we can do the fifth one and sixth one. Okay. Right. For a process running under multitasking kernel means operating system, a page fault or cache miss for a instruction fetch arithmetic operation would cause a context switch or stalling of the instruction. I told you that there's something called a preemptive and non-preemptive. Right? In one approach, we give the fixed time slots. In the other approach, we do the context switching only after if the instruction is over, or maybe now it is waiting for input output, right? Input output. There's another third possibility of context switching in that case, that is you try to access a memory page, and that memory page is in the virtual memory. Now you need time to do the swapping. So therefore, that is another place where you can do the context switching, because you are not doing context switching unless there's a reason, right? So now what are those possible reasons? Page task is over. Now you can do the context switching, right? Or now you are waiting for a user input output. Now you can do the context switching. The third possibility is now when you try to access that page is not in the memory, it's in the memory, virtual memory. Now we need little bit of time to do the memory swapping. So therefore now we can do the context switching and give it to give the opportunity to the another process. Okay. So therefore answer is, for a process running under multitasking kernel, page fault means the page is not there in the memory. That means it has to be taken from the secondary storage. For a instruction fetch, because now you try to access that instruction, but that instruction page is not there, would cause a context switch. This is a good opportunity to do a context switch, right? Because it's now we need little bit of time. So therefore, let other process take the opportunity, right? So those are the three possibilities where context switching can happen, right? Unless you are going for a fixed length. Of course, if it is fixed length, always it has to do the context switching after the time stop. But this is input output operation, page fault, or program is over. Program is executed, finish. Right. Sixth one. Computer memory hierarchy usually works because it upholds the principle of locality of references, which says a reference to memory location will most likely to be reference, and locations be likely to be reference. So there are two localities that we discuss when we were discussing the caching, right? So what are those things? If something is accessed recently, there's a possibility. So say now we access a particular data. There's a high possibility that it will be again accessed. That is one possibility. Second thing is, if you access a particular data, there's a high possibility that the nearby data will also be accessed, right? So what are the two possibilities? If this particular data is accessed, there's a possibility that it will be again accessed. Okay, so that is called locality of reference. Okay, so now let's go back to the note, because this is clearly mentioned in our note also. Locality. You can see temporal locality, right? If items is reference, it will tend to be reference again. Yes, for example, if you are in a loop, say you have loop something like that, so these things you can perfectly understand. Say you have while loop, int x equal 0 while x is less than or equal to 10, print x plus plus. Now you can see that now here x is x axis. Now throughout this loop, again, now here x is axis, again x is axis, again x is axis, again x is axis, again. Now you can see when x is axis, there's a high chance you will access x again and again, especially when it comes to loops. And of course, even when it is not a loop, when you do calculation of something, again that variable might be used below. That is called what? Temporal locality. So when you access a particular data, we keep it in the cache, because assuming that we may need it again. So that is called temporal locality. So the spatial locality means when you access a particular memory location, you don't take only this one. Sometimes you take the nearby data as well to the cache. You really need this one, but you are taking this portion to the cache. Why? That is called spatial locality. If item is reference, items whose addresses are closer by tend to be reference as well. So very good example is if it is array, right? If it is array elements data is in the consecutive location, right? If a first element is access, first element of the array is access, there's a high chance second, third elements are also going to be accessed next. So therefore, when you are taking the data into the cache, you not only take this, sometimes you take the nearby data also. So therefore, when you are accessing the second element, now it is in the cache. So that is called spatial locality, right? Spatial locality. So it's in your note, okay? Right. So that is exactly what they are talking here, right? Right. So the seventh one, a processor which has word length of 64 bits would have virtual or physical memory width of 64, right, or 8 bits, and a register width of 32 or 64 bits. Okay, now look at this. Processor which has a word length of 64 bit. That means processor's word length. That means processor's, that general purpose, the program, the instruction registry is 64 bit. So this is the instruction that you take it from the memory. You take it from the memory. So therefore in memory also it has to be physical memory also. It has to be what? Physical memory, I told you that always 8 bit. Remember I told you physical memory always 8 bit or 1 byte, right? But logical memory or the virtual memory or the logical memory, its width is same as your processor's registry width. Your processor's registry width is 64 bit, right? Processor which has the word length 64. That means your logical memory logical memory width is 64 bit, right? Logical memory width is 64 bit. But I told you physical memory, it's always 1 byte in typical processor, right? In typical processor, I told you at the beginning of the class also, in physical memory, it is always 1 byte in a typical processor, but your logical memory width is same as your processor general purpose registry width. So general purpose registry width is 64 means your logical memory width is 64 bit. Your physical memory width is typically always 1 byte, Okay, so therefore this is 64 because it's a logical memory, and physical memory is always 8-bit. Okay, 8-bit. Right, so next question. A lot of questions are there, right? Okay. A processor which has clock rate of, let me delete this, clock rate of 1.5 gigahertz. Right, clock rate is 1.5 gigahertz. That is R. R is 1.5 into 10 to the power. Kilo is 10 to the power 3, mega is 10 to the power 6, giga is 10 to the power 9 hertz. Okay. CPI is 0.7, cycles per instruction 0.7. What is the MIPS rate? Right? That is millions instructions per second, MIPS rate. Right? So we have a formula to calculate IPS when we have R and CPI. What is that formula? IPS is R divided by CPI. IPS. Yes, IPS is clock rate divided by CPI. Right? So let's calculate. IPS is clock rate divided by CPI. So therefore 1.5 into 10 to the power 9 divided by CPI is 0.7. That is IPS. Right? That is IPS. What we need is MIPS. MIPS is millions of instructions. So million means 10 to the power. So we have to divide by 10 to the power. Million means this one, right? Yeah, so that means we have to divide by 10 to the power 6. So therefore what is the final answer? So this is 6, 3. This is 15 divided by 7 into 1000. Right? 15 divided by 7 into 1000. What is that value? 15 divided by 7 is 214, 10, 1, 7, 30, say 4, 2140, 2140. Right? So I think this they have given it as in a rough value. The real value must be 2140 MIPS. Okay, MIPS. Right? Because it's 15 divided by 7. Okay. Yeah, 2.14. That means 214. Again, if you go for the next one, yeah, 2143, something like 2143. Okay, 2143. Right. So the ninth one. In multitasking operating system, a the process is blocked. Block means it is waiting for input output. Will be moved to the running or ready to run state when the IO activity has completed. Remember, if it is in a block state, why it is waiting for input output? Now once the input output is done, it is going from block state to the ready state, not to the run state, right? Ready to run. It will be moved from that state to ready to run. It will never go to the running directly, right? Thread scheduler has to take it from ready to the running. So it is going from block to the ready state, right? Once the IO activity is completed. 10. In demand paging as applied to virtual memory, physical memory, the most frequently accessed set of page blocks by, right. So demand paging I didn't explain you, it is also mentioned in the note, right? Demand paging. So this is called demand paging. I will explain that when we are doing the caching. Okay, so when we discuss the caching, I will explain the demand paging. Still we haven't done that. Okay, so therefore let's not do that one. Right, so this is again related to the multiprocessors. Right, we haven't done that, and this is also multiprocessor. Of course, this one we can do virtualization. Operating system virtualization allows, that means that with the help of the operating system, or we call it para virtualization, allows the use of multiple, not hardware, virtual machines on top of hypervisor, right? Hypervisor, on top of the hypervisor we can have multiple virtual machines. Okay, so that is operating system work, that is that we discussed last time. Okay, last class. So this is again multiprocessing. Still we haven't done the multiprocessing. Okay, right, so we'll stop at this point, right? So next time we will be doing multiprocessors and related things, and then we will be moving to little bit into the, so there are some few things again, like how the caching is handled, cache replacements, some caching algorithms are there, how do we decide which page to be replaced from the cache, right? So we will be doing those things, and we will be doing bit of C coding also, the thread programming in C and process programming in C also we are going to do. Okay, so now we are, more than half is over, right? Actually I would say, yeah, more than half is over. Now we have to do small topics. Maybe within 2 weeks we will be able to finish this subject. Okay, right, we stop at this point.